All right, let's dive right in. Today, we are taking a fascinating journey, peeling back the layers of code to see how the words we type actually become actions a computer can understand. We're going from the surface all the way down to the core. So it really all boils down to this one question, right? How does a simple command, something that looks a bit like English, make a machine that only understands ones and zeros actually do something? That's the big mystery we're going to solve together today. To get our heads around this, you have to realize there are basically two different worlds of code. It's like a programmer has to choose. Do I speak a language that's easy for me, a human, or one that's easy for the machine? So, at the end of the day, a computer language is just a rulebook for telling a computer what to do. It's the bridge between our ideas and the computer's actions. And pretty much all of them fall into one of two big families. You've got your high-level languages, and you've got your low-level ones. This right here, this is basically our map for today's journey. See how it's layered? Up at the top, you have the high-level stuff, the code that looks familiar. And as we go down, we get closer and closer to the actual hardware, the bare metal. So let's kick things off at the top of our map in the world where most programmers spend their time. We're talking about high-level languages. You see, high-level languages are designed to be, well, closer to our language. They use words you recognize, like if this, then that. And that's their superpower. It means we can focus on the big picture, the logic of our program, without getting bogged down in the nitty-gritty details of the computer's brain. And look, the benefits for developers? They're huge. They're just plain easier to learn and work with. And a really big deal is that they're machine independent. That means you can write code once and run it on a totally different computer. Plus, with tons of built-in tools, you can get a lot more done with a lot less code, which, makes everything way faster. But, and this is a big but, there's a catch. The computer itself doesn't actually speak C++ or Java, so our human-friendly code needs a translator. That's where a compiler or an interpreter comes in. It's a special program that takes what we wrote and translates it all the way down into the ones and zeros the hardware can actually use. Okay, time to go deeper. We're going to descend one level on our map, leaving the comfort of those human-like languages behind. Welcome to the world of low-level languages, where we start speaking the machine's language. A low-level language is pretty much the exact opposite of a high-level one. It's built to be understood by the computer with almost no translation. And because of that, for us humans, it can look incredibly cryptic, and honestly, it's a lot harder to work with. And this slide, it really nails the core trade-off here. On the one hand, high-level is easy for us, but it needs a fancy translator. On the other hand, low-level is tough for us, but it's so close to the machine's thinking that it only needs a much simpler translator, something called an assembler. That's the fundamental difference we're digging into. So now, for the really fun part, we're going to zoom all the way in on the most famous low-level language there is, assembly. This is where we get to see exactly how a programmer can talk directly to the CPU, the computer's brain. Okay, so assembly is basically one tiny step up from pure machine code, from the raw ones and zeros. It uses these simple, memorable keywords, they're called mnemonics, that stand in for those binary instructions, and this gives a programmer insane, direct control over the hardware. So how do we control the CPU? Well, we do it by messing with these things called registers. The best way to think of registers is like tiny, super fast scratch pads right inside the CPU. All the real work, the adding, the subtracting, the data shuffling, it all happens right here. Assembly language lets us put numbers directly into these registers and tell them what to do. Let's look at our first command. It's called MOV, short for move. It's super simple. When you write MOV AX, 6, you're literally telling the CPU, hey, take the number 6 and stick it inside the AX register. That's it. It's the direct, low-level way of doing what you'd write as AX equals 6 in a normal language. Next up, we've got AID. And yeah, no surprises here, it just does addition. The command ADD BX, 2 tells the CPU whatever number is in the BX register right now, add 2 to it. It's the machine's version of us writing BX equals BX plus 2. And to finish off our basic math toolkit, we have sub for subtract. Sub AX, 4 is a direct order to subtract 4 from whatever value is sitting in the AX register. Again, it's just like writing AX equals AX minus 4. So you see, these simple commands, MOV, AD, sub, these are the absolute rock-bottom building blocks of everything a computer does. All right, enough theory. Let's make this real. We're going to step through a tiny little assembly program, one command at a time. So follow along and let's watch what actually happens inside those CPU registers. Okay, here we go, line by line. First up, move AX 0. Bam, the AX register now holds a 0. Next, add AX 6. Easy enough, AX is now 6. Now let's load up the other registers. Move BX 4, okay, 4 goes into BX. Move CX 5, and 5 goes into CX. Now for the interesting part. Add AX BX. The CPU grabs the 6 from AX, adds the 4 from BX, and the result, 10, gets stored right back into AX. Next, sub AX 3. 10 minus 3, that leaves 7 in AX. And now the grand finale, mul BX. This multiplies what's in AX, which is 7, by what's in BX, which is 4. The final result, 28, gets stored in the AX register. And just like that, we've made the CPU do math, step by step. So that was cool. We've written the code, we've traced it out, but how do you actually get a computer to run it? Let's get to our final section and see how all this becomes a real program. You know, the process to bring this code to life is actually pretty straightforward. First, you just write your code in a basic text file. Then, you feed that file into a special program called an assembler. That's our translator, which turns our simple commands into machine code. Finally, another tool called a linker packages it all up into a single file that your computer can actually execute. And that's it. That's the whole journey. We start with these human-friendly shortcuts like MOV and ADD. The assembler and linker then translate them down into the pure ones and zeros that the CPU can execute directly. We've gone from the very top of our map all the way down to the very bottom. Which really brings us to the final big question. If high-level languages are so much easier, so much more efficient for us to use, why would anyone bother with all this? Why do we still need to speak the machine's native tongue? Well, it's for those times when you need every last drop of performance, or you need to control the hardware directly. Think operating systems or super fast video games. It's the ultimate trade-off between our convenience and the raw, untamed power of the machine.